Hey, hi guys, good morning.
Good morning, sir.
Good morning, good morning. Sorry guys, my apologies once again. So we'll try to cover up, in this week. So if you guys are okay, then we can have a session from 8 to 10, if that works for everyone.
We can, sir.
Okay, sure. All right, so where we stopped, I think in the last class we discussed about probability. So we'll continue from there. Okay, so okay, a quick recap and then we can continue. Okay, so probability, it's a measure of the likelihood of any event to occur. And this whole in data science, probability is a very important topic. Basically, in machine learning and even in statistics, we majorly depend on this probability. So in statistics, you might have seen that, okay, we discussed about Z distribution, we discussed about T distribution. So all that distribution are nothing but called as probability distribution. So here with this distribution, we can able to understand that what is the probability that any particular number may occur, okay, and what is the chance of that? Or if it is a continuous variable, then what is the probability that any value would be between this range? Okay, so we discussed about that confidence interval and all those things. Those are nothing but the output of this probability. So, in a nutshell, if any, whatever kind of event, okay, we are talking about, whether occurrence of any particular number or whether it could be any number falling in particular range or any particular categorical event occurrence. So it all kind of falls under probability. And even when we get into machine learning, there also whatever algorithms we are going to cover in terms of predictions, those are also would be based on probability. Because see, when it comes to predictions, so predictions by name itself, it is all about guessing something, okay, right? So guessing of any event occurrence. So generally, it would be probability only. It would be what could be the likelihood of that particular event to occur. That basically would be the output of these predictive models. In that way, probability is considered as the very important topic in this data science. And if you have any um, questions in terms of understanding this probability, feel free to ask me and then there itself, because this would be the base for rest of the other topics. Okay, so probability is a numerical measure. And it ranges between 0 to 1. So if the probability values is towards 1, then there would be high certainty. And if it is towards 0, then it would be more uncertain, okay, of, to comment on any particular event. If it is like zero point 0.5, then that means you are not even certain and you're not even uncertain, okay, about that. So you are somewhere in between. So if I'm saying if there is a probability of 0 of any team to win, so that means it's quite uncertain, or it's very less likely that particular team would win the match. Okay, when I'm saying it's towards 1, then it's quite certain that team would win the match. But if it is like probability is 0.5, and in data science, this is the more of a risk area. If through any of our analysis or through any of our predictive models, if we reach to this particular point, like where my model is predicting with zero point 0.5, like 50% probability, in that way, that model would be of no use. Because in that way, you cannot decide whether that event would occur or whether that event would not occur. So it would be somewhere in the middle. And in that kind of scenario, you won't be able to make any kind of decisions. So generally, we we try to do the analysis in such a way that, okay, either the probability should be closer to 1 or should be closer to 0, so that it would be it would be easier for the business to make decisions based on the output of these models. Okay, so classical probability is nothing but the number of occurrence of a particular event divided by total number of outcomes. So, so for example, you have to find out how many times a machine, what is the probability of the machine to fail. In that case, you need to understand what should be the size of your sample for your analysis. Let's suppose you have taken 100 such scenarios or 100 days or 100 hours of uh, um, machine outcomes, and then the total space, sample space would be denoted by capital N. And in that particular space, sample space, how many times that machine failed, that would be your small ne. Okay, so that is the number of events, okay, which has occurred in this particular sample space. Now that would be a probability. So in this case, for example, out of 100 observations, 10 times the machine failed, so the probability would be 10%. Okay, so 10% chance. So that's how we calculate the probability, and we are aware of this method. So this is known as classical probability. So this we will discuss relative frequency and all those things later. Okay. Now then we went into this terminology. So like experiment, event, elementary event, sample space. So this we will discuss one by one in detail. So experiment is nothing but a process that produces outcomes. For example, now you are making you want to test a drug. Okay, that what is the chance of that drug, that it would react positively on any of the health disease. So in that case, every time whenever you are giving a medicine to the individual, that become your experiment. And once you have given that medicine to a particular individual, then you will measure the outcome, whether that particular medicine worked in a positive way or the negative way. Okay, so this process of giving medicine, or a process that produces outcome, is known as an experiment. So typically, uh, when we perform any kind of a test, we go with multiple trials. Okay, so experiment is just a process. Okay, that giving a medicine to an individual. But how many times you have to perform this experiment? So that is nothing but a trial. Okay, and for every trial there would be an outcome. Okay, so one such outcome is known as elementary event. Okay, so overall, if you look out for overall, if you measure the outcome, that is known as event. But for every trial, if you measure the outcome, that is known as elementary event. Okay, so this event you can tie up with an experiment, and this elementary event you can tie up with the trial. Okay, so that's how you can relate these all terminologies. So now let's suppose this is an example. So there is one tiny town, okay, just for the example, hypothetical situation, that in that particular town, okay, there are only four families, which stay there in that town. So let's suppose there is a family A, B, C, and D. Now, there is another column which states that whether the children is there in that particular household or not. Okay, so out of four, three families, they have childrens. Okay, and this third column says number of automobiles. Okay, how many vehicles each of these family they have, that is stated here. So here the experiment is randomly select without replacement two families from the residents of the tiny town. So now this is the entire population, and from here, I want to draw a sample. Now I want to just draw a sample, or I want to pick up certain families, like two families, and I want to find out, two two families I want to pick up, which has here, there is no such condition, randomly select two replacement, two families from the resident. So I just randomly want to select two families. Okay. Now the elementary event is the sample includes family A and C. Now here I'm talking about the outcome. Okay. If I'm selecting randomly two families, now I want to know that whether that those families includes A and C in my sample. Now event here is each family in the sample has a children in the household. Or it could be the sample families owns a total of four automobiles. So overall, if I'm talking about the experiment, that is known as event. If I'm talking about a particular trial, so for example, I picked one family, whether whether that family is either A or C, that depends on that particular each trial. So that becomes your elementary event. Overall, from all the entire experiment, if I want to make a judgment that okay, these families, each of these families has a children, or each of these families owns total of four automobiles or not, that is the total outcome of my experiment. So that we called as an event. Okay, understood. So in one particular experiment, consider that there could be multiple trials. So for example, if you want to launch a vaccine, so you go with the multiple trials. We call as a clinical trial, right? We conduct that experiment on multiple different creatures and then individuals of different age and gender. Okay. So then each process of that experiment is considered as a trial, and every trial will have an outcome. So whether that vaccine passed or vaccine failed, right? And collectively, overall, if you take that whole experiment of that 100 trials or 1,000 trials, and then on based on that, if you say that 90% of the trials passed, now that will become the event of that particular experiment. Okay. Now, sample space sample space you can consider as the entire uh, scope of that experiment. For example, the number of trials you have conducted in a particular experiment as 1,000. So 1,000 would be your sample space. So every outcome, elementary event of that particular sample will create your entire sample space. Okay. So it will become a set of all elementary events coming out from every trial of an experiment becomes your sample space. So now there are multiple methods. So if you have to calculate the probability of any particular event to occur from the entire experiment, then manually there are multiple ways of doing it. Okay, so one way is like roster or listing method. Second is the tree diagram, then set builder notation, Venn diagram. There are multiple methods, and all these methods possibly you might be aware of or you have seen it somewhere. So we will just touch upon that. But through this programming now, all these things have become much more easier. You need not to go and use pen and paper to do all these things manually. Okay, so all these things can be done programmatically by using tools and technologies. Okay, and you can compute it very quickly. Okay, so now for example, this is my entire population, and from this, let's suppose I'm selecting something, randomly selecting a sample. So here the experiment is randomly select without replacement. I'll tell you what do you mean by without replacement. I'm selecting two families from this resident. So here, when I do this experiment, I will can go ahead with multiple trials. So first trial may give me AB, second trial may give AC, third trial may give AD, okay, like this. So this is all the list of possible combinations I may get, if I have to select two samples. Without replacement means every two select would be different, okay. With replacement means, so let's suppose there is a box. In this box, there is A, B, C, and D. Now, with replacement means I'll pick one blindly, okay, randomly. Let's suppose I picked A, and then I will put it back again. Okay, so with replacement means I'll put it back again. So there is a chance that again, if I'm going and picking, I may get A again. Okay, so that is with replacement. So with replacement, I may get the same output again. But without replacement, I will get a always different outcomes, okay, from my trials. And together, the outcome of all the trials will be considered as my sample space. So Now, this is my overall sample space, and anything apart from this, I may not get it, right? Any other combinations. I may either get a combination like this, and this. So the total size of my sample space is how much? 1, 2, 3, 4, 5, 6. It's 12. Okay. So now so basically this is my, and if you remember the probability equation, it is NE by N, where N is nothing but my sample space. So this is important for you to calculate the denominator, to find out the probability. And then based on that, we can, whatever thing we want to calculate or we want to basically analyze accordingly, we can decide on this NE. Okay, so another another way, this is basically a roster method, okay, where we are kind of identifying all the possible combinations and then listing it in the roster. So that is known as roster method. Second is known as tree diagram. This is out of all, this is my favorite. This is simple. So now you have these four families. Okay. Now with this A, what all you can pick? You can pick either B or C or D. Okay. So these are the three combinations you may get if you pick A first. Okay. Then if let's suppose you picked B first, then later after B, either you can pick A, C, and D. So similarly for C and D. So now this would become A, B, this would become A, C, this will become A, D, this will become B, A. Here order matters, right? Uh, okay, so these are all combinations, different kind of combinations which I can get if I have to pick up two families out of these four. So overall, how many you will get? You will get 12. Now this is my sample space. Through this roster method, through this tree diagram, you can identify the sample space. Now this is Venn diagram. Okay, 1 second. Okay, let's take an example. Okay. Now tell me, guys. So now let's suppose this is your sample space. Now tell me, what is the probability that you will choose uh, family C? What is the probability that you will select family C? How you will calculate?
6/12.
6 by 12. Is that
Uh,
correct? Others? So that's correct answer, because see, out of this is your entire sample space. In this sample space, you have to see how many times C may occur. Okay, so this is 1, 2, 3, 4, 5, and 6. So out of total sample of 12, there is a chance of selecting 6. C is 6. Okay, so then 6 by 12 is your probability of selecting C. Now I can make it little more difficult for you. If I say, what is the probability that, okay, a family has a household, has a children? The combination of the families have children. So now you have to go and find out the combinations of like either A, B, and D. Okay, so wherever C is not present, you will take all that combination, and now that will give me the probability of selecting the families which have children. Similarly, for the number of automobiles, you can find out the probabilities. Okay, so first major problem is all about the sample space. Okay, what could be the sample space? Denominator is more important, and denominator, these are the techniques through which you can find out the denominator, either through roster method or through tree diagram. Okay, now you might have heard about set theory, right? So set theory again is a subset of probability. So here we need to understand whether these sets are independent or dependent. Okay, so if they are independent, then we'll see, how we can compute probability. If they are dependent, then we will see that how we have to change our approach in terms of finding out the probability. If they are independent, then we directly go and find out the marginal probability. If it is like dependent, then we go with conditional probability. Okay, so we will understand that, step by step. So let's suppose these are the two independent events. Okay, so like 1479 and 23456. Okay, now here, if you have to find out the union of these two, okay, the outcomes of these two events, then all the possible outcomes of each of these events, will become your x union y. Okay, here in this case, this apple is the common. Okay, so if these are the two events, the entire space of this is known as your sample space, in which there could be certain events which would be part of both the events, okay, which we call as a intersection. So here in this two events, in the two sets, basically the 4 is kind of common, okay, which we call as an intersection. So here x intersection y will be equal to 4. If they are completely independent, if they are not, if you don't have any common elements in the two sets, then your x intersection y will be equal to 0, because you don't have any common elements in both the sets. Okay, in this case, its intersection is apple. In this case, you do not have, it's null. In this case also, it's null. Okay, it will be equal to 0. So now this is important, for you to understand whether the intersection is 0 or not. Because if you understand this, uh, whether the intersection is 0 or not, you can define whether these events are independent or dependent. Okay. And we have discussed about this mutually exclusive and collectively exhaustive, right? So when we saying mutually exclusive means these two events are mutually exclusive. That means these two events will not occur together. So in that case, your x intersection y will be equal to 0. So in this way, you can understand whether your events are mutually exclusive or not. Independent events, the definition of these independent event is the occurrence of one event does not affect the occurrence of or non-occurrence of the other events. Okay, so for example, you are rolling a dice and you're tossing a coin. So these two are completely independent events. So there is no no dependency on each of these events. So occurrence of one event will not affect the occurrence or non-occurrence of the other event. The conditional probability of x given y is equal to the marginal probability. So what does that mean? Okay. So here the probability of x, given that there is another event occurred, will be equal to px only, because here this y is not impacting this x. So these are two independent events. Here these two events are not impacting each other. In that case, your conditional probability, this is denoted as conditional probability, and this is known as marginal probability. Let's take an example. Okay. Okay, let's take an example. Okay, what is the probability that there would be a traffic jam? Okay, given that it is raining. So if traffic jam and the rain, okay, if they are dependent on each other. So for example, if it rains, there is a high traffic. If it does not rain, then there is a low traffic. Then there is a dependency. Then the probability of getting a traffic would not be equal to a marginal probability. It would be it would be calculated in a different way. Okay, it would be not just like, out of all the days, how many times there was a traffic, and that would give me the overall probability of the traffic jam scenarios. It would not be that simple, because here we have to consider another event which is driving my traffic. Okay, let's suppose if it is like some other event, like what is the probability of a traffic jam given some independent event, given that uh, inflation is high, okay, or stock market is high. So there is no connection between these two events. In those cases, these two events are considered as independent, and in that case, your marginal probability would be px, and it would not be impacted by y. So the conditional probability of x given y or y given x is will be equal to the marginal probability if the x and y, these are independent events. Okay. Complementary event is, see, now we have a sample space. Sample spaces is all the possible outcomes from an experiment is known as sample space. And this sample space, all the events are together known as collectively exhaustive. What is collective exhaustive means? For example, I'm rolling a dice. Okay. If I'm rolling a dice, my sample space would be 1, 2, 3, 4, 5, and 6. Would I get any other outcome apart from these 6 events? No. So this becomes my sample space. And why we are saying collectively exhaustive is because the probability of each of the events, if you sum it up, will be equal to 1. Okay. So the probability of this entire sample space would be equal to 1, because probability of every event, okay, elementary event in the sample space is equal to 1 by 6, right? And if you add all these probabilities together, then it will give me the uh, overall probability as 1. So what is the complementary event? So complementary event is, for example, out of this entire sample space, now this is my event. Okay. So any event other than this possible event will become my complementary event. So for example, in this case, let's suppose I take 1 as the event. So that is my event. So complementary event would be all other events apart from this particular event 1. Okay. So in that case, if the probability of this event is 1 by 6, then probability of complementary event would be 1 minus 1 by 6, because all these other events will become the complementary events, and the probability of each of the events would be 1 minus 1 by 6. Okay, so this is how you calculate the probability of the complementary events. Now counting the possibilities. Okay, so now, for example, so now this is important, guys. Counting the possibility. For example, when you are dealing with any kind of an experiment, you need to understand what could be the total number of possibilities or possible outcomes which could come up, out of this particular experiment. That again you can calculate through multiple ways. There is MN rule. There is if you are sampling with replacement, then there is a separate method. Without replacement, there is a separate method. Okay, so let's first understand the MN rule. For example, if an operation can be done in M ways, and the second operation can be done in n ways, then there are total m into n ways of the two operations to occur in order. Okay. So, for example, if I say there to reach from a particular origin to reach a destination. Okay. The first way is like first you have to reach here. So there are m ways, to. So there is m route. Okay. There are m ways, to reach to this particular point. From again to this point, again you have multiple ways, n ways. Okay. Now, if I say what is the total possible options, okay, for you to travel from this particular origin point to destination point, then total ways are m into n. So if this is 4, if this is 3, then there are 12 ways, possible ways, through which you can pass from origin to destination. Okay. Now this can be easily extended to whatever number of stages. Now here we have just shown two stages. Now there could be there could be multiple k stages. Okay. Then it would be n into n2 till nk. Now this will give me the total sample space. Now this is important in terms of you to decide what could be the size of your experiment. Okay, what could be the total number size of your sample space, right? In that way, you can able to understand what could be your numerator. Okay, when you have to calculate the probabilities. So, for example, if you want to toss two coins, what would be the total sample space? So there would be a two possible outcomes from one particular experiment, and from other experiment, again two possible outcomes. The total would be four. So you can either you can use this tree map, to find out these possible outcomes. For example, from first coin, either you will get heads and tails. From other coin, you will get head and tails. So either you will get both the heads, or you will get first time you will get heads and second time tail, first time tail, second time heads, or tail tail. So this is your overall sample space. Okay, you will not get any other combination apart from this. So either you can use this tree diagram, to come up with this, or else you can use roster diagram, roster method, or else you can use this M rule, MN rule. MN rule says that okay, in one coin you have two possible outcomes, in second coin you have a two possible outcomes, then you will have a total four outcomes. Okay, as your entire sample space. Okay, now sampling with population with replacement. So I'm just giving you the uh, understanding about how basically all these things are calculated. Okay, ultimately, we have to use each of these techniques, to finally solve our problem. We need to understand, okay, whether we have to find out the sample space, whether we have to go with MN rule, or we have to go with this with replacement technique, or without replacement, and then find out the sample space. So finding the sample space is very, very important, very critical, because if you do not understand what could be the size of your sample, then calculating the probability would be difficult. Okay. So in this case, let's see, a tray contains 1,000 individual tax returns. So for example, in any income tax office, on a particular table, let's suppose on it in a tray, there are 1,000 individual tax return forms. Okay. If three returns are randomly selected, okay, with replacement from the tray, how many possible samples are there? So here, very important is with replacement. So what does that mean? Okay. So there are 1,000 tax returns so now I want to pick only three out of all these 1,000. So let's suppose I picked one. Okay. Let's suppose I mark it as A. With replacement is again I'm putting it back. Okay. So there's a chance that I may pick A again. So in any combination, I may get double A or triple A also. Okay. Multiple times I may pick a same form again and again. So that is a chance. If that's the case, how many possible samples I may generate out of this particular experiment? So it is denoted by n raised to the power small n. The small n is nothing but my sample space, which is sample size, which is my three returns. Out of this 1,000, I want to pick only three. So I'll keep picking three. Okay. So now this would be my entire sample space. Okay. So see how big it is. Now, if I'm saying without replacement, then I have to go and find out the combination. So the combination formula is NCN. Okay. If you remember, it is factorial of n. I know, I think you guys know about factorial. Okay, so factorial of 5 is nothing but 5 into 4 into 3 into 2 into 1. Okay, this is factorial. So if it is 1000 so here it is 1000 of factorial divided by factorial of 3 into 1000 minus 3, which is 997, 997. Okay, so this would be the number of possible samples if we are going without replacement. So without replacement means every time I will select a unique form. Okay, in the group of three, if I have to select every time, if I have to make sure that form whichever I'm selecting is not getting repeated, so in that case, I will go without replacement. So there I will use the combination technique, which is NCN. So there is a difference. So you need to understand for any particular kind of a problem, whether it is a with replacement problem or without replacement problem, and accordingly you have to select these techniques to find out the sample space. Finally, different types of probabilities. Marginal probability we have discussed. It is completely whenever we are discussing about any independent event. So completely independently, if we find out the probability of particular event, that is known as marginal probability. So union probability is a collection of both the events together. Okay, what is the chance? What is the occurrence that all these events in these two experiments would occur? So that is known as probability of X union Y. Okay, we will add the probability of all those possible outcomes. The joint probability is nothing but the intersection. Okay, joint probability where whatever events from these two experiment which will occur together, okay, is known as joint probability. Okay, so probability of X and Y occurring together. Conditional probability is when one event is impacting the other event, then we call it as a conditional probability. So don't worry, we will talk about each of these probabilities with example. Okay, just for the definition purpose, I'm showing you the slide. So the probability of X occurring given that the Y has occurred. So now this conditional probability is very, very important. Okay, so usually whatever we uh, try to find out in the space of data science, we generally deal with conditional probability. Why? Because the businesses would want to understand which of the events are driving which kind of events. For example, I want to increase my sales. So firstly, I need to understand what kind of events are driving my sales. So sales are conditioned to what kind of events. Now, conditional probability would help them, to decide where to focus and, where to not. Okay. So if the sales are getting driven based on the price change or based on the any other factors like discount or any promotional activity, there we can say that, okay, what is the chance that my sales will go up that given that, okay, if I run this kind of campaign. So based on that probability, I can decide which campaign to run and which kind of promotions I need to focus, to drive my more sales. Even for operations, in the operation side also, for example, machines monitoring. So I need to understand, okay, if the machines are getting failed, why they are getting failed? Okay, they're conditioned to what events? So what is the probability that machine fail given that it has ran for more than 10 hours or 12 hours? So in the from a business point of view, conditional probability plays a very important role in terms of giving information like what events are impacting your other events. Okay. And when we talk about machine learning, guys, there would be multiple events. So we will see that, how you can build a predictive model given you have an information about 20 or 40 variables. So based on those and 20, 40 variables, what may occur? Okay, that that's something, okay, we'll see in the machine learning classes. So let's suppose I'll give you an example. What what is the chance that customer will buy a product given that he has logged on to website at this particular time and he was on the website for this many hours, given that he is a male, given that his age group falls between 40 to 50, given that he belongs to this particular region. So like that you will have 40 or 50 attributes of that customer, and this machine learning algorithm, based on all these different events, it will find out the probability whether this person will buy a product or not. Okay. So that is known as conditional probability. Okay. Which basically these machine learning algorithms will try to uh, learn and predict, from the data. Okay, so now in probability, we have two basic laws. One is law of addition, and the second is law of multiplication. Okay, so we will understand what is law of addition now. So basically, law of addition is used, for finding the union part, probability uh, of two or multiple events, um, to occur. So not together, but what is the probability of every event in this entire sample space, okay, together is known as union. So if I have two events, okay, the probability of X union Y will be given as probability of X plus probability of Y minus probability of X intersection Y. Why we are doing this? Okay, so let me show you simply. One, two, three. Let's suppose these are the three outcome of these particular experiment X, and there is 2, 4, 5. These are the outcomes from this experiment Y. Okay, so probability of X can be given as probability of 1 plus probability of 2 plus probability of 3. Okay. So probability of Y is given as probability of 2 plus probability of 4 plus probability of 5. Okay. Here, if you see, this probability of 2 is kind of repeating two times. Okay. So I can mark it as like this, right? 1, 3, 4, and 5. And this is 2, which is common in these two experiments. So if I want to find out the union, I have to find out the probability of 1, probability of 3, probability of 2, probability of 4, and probability of 5. So if I sum these two up, if I just say px plus py, this probability of 2 will be counted twice. Okay. So to avoid that, what we can do is we say probability of x, so which is, I say that probability of 1 plus probability of 2 plus probability of 3 minus probability of 2 plus probability of 4, probability of 5. Now this 2 is occurring, we are considering twice. So what we'll do is we will take the intersection of these two, which is prob 2. Okay, we say probability of 2. Now this will cancel out. And now this will give me the total probability of X and Y. So which is known as X union Y. So if this X and Y are independent, so if they are independent, that means there wouldn't be any kind of an intersection. So this part will become 0. In that case, the probability of X union Y would be probability of X plus probability of Y. Okay. So now this something, okay, we need to understand whether the joint probability is 0 or not. If it is 0, then that means the events are independent. If it is non-zero, then that means the events are not independent. Okay, so now take this problem. So now suppose a company has conducted one survey, okay, for a particular American Society of Interior Designers, okay, in which the workers were asked which changes in the office design would increase the productivity. So this is the entire community, okay, of designers, who work inside, and they think creatively, to come up with some kind of designs or something like that. So now here the question is that they are asking these people, okay, in the office, what kind of changes need to be done, okay, so that overall the productivity of employees increase. So they have given two choices. One is if we reduce the noise, if we kind of make the whole office uh, noise free, and in that case, would the people would concentrate more, and ultimately, eventually, whether that would increase the productivity or not, or more storage space. Okay, more storage space means if they increase the size of the office, okay, and so that that may increase the productivity. So they have just given the two choices, okay, and they've asked the people, to fill that survey. Now the question is, what is the probability that this person would select reducing noise or more storage space? Either this or this. What is the chance? So based on my sample space, I can think about, like, how many people, okay, may either select this or that, okay, based on the survey responses. Let's suppose N represent the event as reducing noise. Second, S represent the more storage or more filling space. The probability of the person responding with N or S. Okay, so these are the two different events, and I'm finding out either of these. Okay, what is the chance people may give? Okay, so then I'm discussing about the union. I'm not saying and means both the events occurring together. Then I'm talking about probability of N intersection S. If I'm saying either of these, then it is or. When if it is or, then it is N union S. Okay, this is something you need to keep it in mind. So now I understood that this is something, okay, I need to calculate. Sorry. So now I'll go with this law of addition, which is for union. So for the what is the law of addition? N union S is probability of N plus probability of S minus probability of N intersection S. Now in the problem, what they have given is, out of entire sample, okay, 70% of the people, they have opted for noise, okay, and 67% have opted this. So it is very clear that, okay, there are few people who have opted both. It is not 50% and 50%, right? It is 70 and 67. So there are people, who have opted both here. Now let's suppose that information is also given. So they have said that, okay, there are 56% which have opted both N and S both. So that is an intersection. So now we have this information. With this information, we'll just substitute this information into this equation, and we can able to calculate this N union S. So here Pn is 70%, probability of S is 67%, probability of N intersection S is 56%. This I will substitute, and it will give me a answer for N union S. So the probability of a respondent either selecting N or S is 0.81, 81%. Now we can even calculate this, we can have this probability matrix. See, one person selecting, uh, so any person, for any option, there would be two outcome. Either he will select that or he will not select that. So there are two choices which I have given. One is storage space and second is the noise reduction. So percentage of people selecting both is nothing but the intersection, okay, which we have seen, which is 56%. Selecting only one, okay, for the noise reduction, it is 70%, and for storage, it is 67%. So if we put that into this kind of a probability matrix, so like we have only these three information, but rest of the other information we can easily calculate through this probability matrix. So for example, this, what is the probability that a person would select noise but not select storage space? So this is something I can calculate by subtracting 56 from 70. So I'll get 14% here. This also I can easily calculate what is the probability that a person would select storage but not noise. Okay, that is 11%. So like this, if you create this kind of a probability matrix, you can able to calculate the probability for other scenarios as well. Okay, what is the probability that people will not select noise? Okay, that is 30%. What is the probability that people will not select storage? Okay, that is 33%. So this is how, by constructing this probability matrix, you can calculate a lot of other information out of that. Okay, so this is overall what we discussed. Okay, this conditional probability we will discuss tomorrow. Let me know till this point, is everything clear? Now this Pn and Ps is known as marginal probability. This is known as joint probability. Right. So we have four different types, right? One is marginal probability. Second is, and this is known as union. This is marginal. So we understood what is marginal, what is joint probability, what is union probability, right? So tomorrow class, we will discuss about conditional probability. Okay. So it's important for you to understand what exactly you want to calculate. Okay. Whether it is a conditional probability, whether it is a joint probability, that's something you have to be very clear. Okay. If that is clear in the mind, you can able to uh, use the right method for calculating that. All right. So tomorrow we will connect at 8, guys. Okay, sharp at 8. Okay, and we will continue till 9:45 or 10. Okay, and that's how we'll try to cope up in this week. If anybody has any concern, then please drop me a message. Yeah, 8 a.m. in the morning. Okay. If anybody has any concern or any issue joining the class at 8, then let me know on the Telegram channel. This is only for temporary purpose, guys, for just this week. And from following week, guys, if you guys are comfortable, we can take the class from 8 to 9. 8 to 9 is also fine. If people who are going to office, if they are facing challenge in terms of joining the class at 9, then we can shift it 1 hour before and we can have it from 8 to 9. Okay, so think about it, let me know. If that is comfortable, then we will move the class little early. Perfect. Okay, so I'll drop a message also on the channel. Okay, so tomorrow we are connecting at 8. Fine. All right, guys, then thank you. Thank you. We'll connect tomorrow. Bye bye.